Welcome to Chapter 6, where we study linear regression. It is one of the oldest and most useful methods in statistics and machine learning, and a natural first step into supervised learning. Linear regression is almost always the first supervised method worth learning. In this chapter, we will develop both simple and multiple linear regression from the ground up. By the end of this chapter, you should be able to explain what linear regression does and when it fits, tell simple from multiple regression apart, interpret slope, intercept, coefficients, and residuals, and understand least squares as minimizing a loss function. You should also be able to train and evaluate a regression model in Python. Interpret coefficients carefully without reading them as causal. Judge models with MAE, MSE, RMSE, and R-squared, and recognize the assumptions and limits, including multicollinearity. This figure shows the core idea. Simple linear regression fits the single line that minimizes the sum of squared residuals, those gray gaps between the observed points and the line's predictions. So, what is linear regression? It is a supervised method that predicts a continuous numerical target from one or more input features. Once you start looking, regression problems are everywhere. Think of predicting house prices, forecasting product sales, estimating tomorrow's temperature, predicting a delivery time, estimating customer lifetime value, or predicting medical costs. What unites all of these examples is that the answer we want is a number on a continuous scale. The simplest version uses a single feature to predict the target. We write the prediction as y hat equals b0 plus b1 times x. In that equation, y hat is the predicted value, x is the input feature, b0 is the intercept, and b1 is the slope. The intercept b0 is the prediction when x is 0, where the line crosses the vertical axis. For a price model, a positive slope says larger apartments are predicted to cost more, which matches our intuition. The slope and intercept are the two parameters the model learns, and reading them is half the value of regression. If sales equal 1,000 plus 5 times advertising, the intercept is 1,000 and the slope is 5. A residual is the gap between what actually happened and what the model predicted, actual minus predicted. A positive residual means the model aimed too low. A negative one means too high. And patterns in the residuals tell us the model has missed something. How does the model choose its slope and intercept? For each observation, we take the squared residual, and least squares picks the parameters that make the sum of those squared residuals across all training examples as small as possible. The least squares idea is easy to state, but it becomes easier to trust once we have ground out a fit by hand. Here's our small data set, 5 days of temperature and iced drink sales recorded at a cafe. The closed form least squares line uses each value's distance from its own mean. With the means in hand, we build a small table of deviations, 1 row per day, and sum the last 2 columns. This deviation table does the arithmetic for us. The squared x deviations 64, 16, 0, 16, and 64 add up to 160, while the cross products add up to 432. Substituting those two sums, the slope is 432 divided by 160, which is 2.7, and the intercept works out to minus 5.6. So the fitted line is y hat equals minus 5.6 plus 2.7x. Here we lay out the predictions and residuals. Notice that the residuals sum to exactly 0, a built-in property of any least squares fit that includes an intercept. This figure shows the cafe data with its least squares line. The gray sticks are the residuals, and the points straddle the line, because least squares forces those residuals to sum to 0. This short snippet computes the same fit directly. It forms the deviations from the means, applies the closed-form formula to get the slope and intercept, and then reports r squared, recovering 2.7 and minus 5.6. The closed form is ideal for simple regression, but it has two drawbacks. An alternative writes the loss as the mean squared error and improves the parameters step by step. Gradient descent updates each parameter by nudging it in the direction that lowers the loss, subtracting a small step proportional to the slope of the loss with respect to that parameter. The learning rate alpha fixes the size of each step. On the small cafe data, both routes reach the same answer. The closed form gets there in a single step, while gradient descent creeps toward it over many small updates. This figure draws gradient descent as a loop. Predict, compute the mean squared error and its gradient, update the weights, and repeat until convergence. The very same loop, with more parameters, scales to far larger models. Real predictions rarely rest on a single feature. Multiple linear regression extends the line to many inputs. Y hat equals B0 plus B1 x1 plus B2 x2, and so on through all the features. Here y hat is again the predicted value. The x terms are the several input features. B0 is the intercept, and each remaining b is the coefficient attached to one feature. A richer house price model might combine floor area, number of rooms, building age, and distance to the city center. Multiple regression is more powerful precisely because it can weigh several pieces of evidence together, letting each feature add its own adjustment. In a multiple regression, each coefficient measures the relationship between one feature and the target while holding the other features fixed. That little phrase, holding the others constant, carries a lot of weight and is where most misinterpretations begin. Here is a key point. A regression coefficient describes an association, not a cause. The model can tell you that price and proximity to transit move together in your data, but not that moving a building closer to a station would raise its price. Establishing causation needs careful study design. Linear regression is simple to use, but it rests on a few assumptions that are worth knowing even when you are using it purely for prediction. The main assumptions are linearity, independence of the observations, constant variance of the errors, limited multicollinearity among the features, and errors that are approximately normal. In a machine learning setting, we often care most about prediction, but violated assumptions still bite, so they are worth keeping in mind. Multicollinearity is when two or more features are highly correlated with each other, and its practical danger is unstable coefficients. When it bites, you can drop one of the correlated features, combine related features into one, or use regularized regression such as ridge or lasso. Another remedy is to apply dimensionality reduction, a topic we take up later in Chapter 13. Plain least squares does not strictly need feature scaling to make predictions. It will happily mix square meters with kilometers. But scaling becomes important the moment regularization enters the picture. Linear regression is linear in its parameters, but that does not chain it to straight lines. By adding terms like x squared as new features, the same machinery can bend to fit curved patterns. A regression model needs numerical report cards, and four metrics do most of the work. Mean absolute error is the average size of the errors in the target's own units. Mean squared error averages the squared errors and punishes large misses. and RMSE is its square root back in the original units. R squared is the fraction of the target's variation the model explains, where 1 is perfect and 0 is no better than predicting the mean. MAE is the most intuitive, while RMSE is the one to watch when large errors are especially costly. Linear regression earns its lasting popularity through real strengths. It is easy to understand and explain, fast to train even on large data. Its coefficients are interpretable. It makes an excellent baseline, and it does well whenever the relationship is roughly linear. It also has real limits. It can badly underfit strongly nonlinear data. It is sensitive to outliers because squared errors give them outsized pull. Its coefficients turn unstable under multicollinearity. It assumes a simple additive mix of features, and it often needs feature engineering. This balance of strengths and weaknesses is exactly why linear regression is so often the first model we reach for. Let us turn to Python. We start with a single feature model on a small synthetic data set where we control the true relationship and can check that the model recovers it. This code generates synthetic housing style data where price rises with size plus some noise, splits it into training and test sets, and fits a linear regression model to that single feature. Because we built the data so that price truly equals 50,000 plus 200 times size plus noise, we can confirm the model recovers something very close to that relationship. This second example moves to a real data set, loading the California housing data, splitting it, fitting a model on all of the features, and then measuring its error with MAE and RMSE. Unlike the single feature toy model, this one leans on all 8 features at once to make its predictions. Consider a case study. An online property platform wants to suggest a price the moment a seller lists a home using floor area, bedrooms, age, location, transit distance, and nearby sales. They need a model accurate enough to be useful and transparent enough to explain to sellers and regulators. Linear regression is the natural place to start, and not only because it is quick to build. The team is careful about 3 things this chapter has stressed, and the result is a baseline that stays honest about its own limits. The following code reproduces that transparent baseline, scaling the features and comparing ordinary least squares against 2 regularized variants on the California housing dataset. Here the code builds a pipeline that scales the features, then trains 3 models side by side, ordinary least squares, ridge, and lasso, and prints their MAE and R squared so we can compare them directly. Comparing the MAE and R squared columns across all 3 models reveals whether regularization meaningfully changes the predictions on this particular dataset. To summarize, this chapter introduced linear regression, the workhorse for predicting numbers, and a gateway to supervised learning. We learned to read slope, intercept, and residuals, to treat coefficients as associations rather than causes, and to respect its assumptions. If you want to go further, look to Introductory Statistics text on least squares, the scikit-learn documentation on linear models, applied text on regression and feature engineering, the original ridge and lasso papers, and case studies on housing and sales forecasting. That brings us to the end of Chapter 6 on linear regression. In the chapters ahead, we build on this foundation toward richer models.